Hello everyone and welcome to Thinking with Mathematical Models 2.5. Today's target, we want to be able to use your knowledge about linear models, equations, and inequalities to be able to solve problems. ACEs for 2.5 are 26 and 31 through 34. Not too bad. So 2.5, amusement park or movies. What should we do? And we're talking about intersecting linear models. It tells us that a company owns two attractions in a resort area. Big Fun amusement park and come on, Get Real movie multiplex. At each attraction, the number of visitors on a given day is related to the probability of rain. And down here we have a little table, and it tells us the probability of rain, or the percentage chance there is to rain, and it's going up in increments of 20. So it tells us attendance for each one at 0%. Chance of rain, 20% chance of rain, 40%, so on and so forth. Goes on up. And it tells us that what the attendance has been at both the Big Fun amusement park. If there's a 0% chance of rain, there's 1,000 people that generally attend. And as the probability of rain goes up, the attendance at the amusement park generally goes down. Okay, so as this one goes up, this one is going down. But at Get Real Movies, as the probability of rain increases, then also the attendance at the movie theater, because it's inside, also increases. Okay, so this one's going down, this one's going up. So it says the company wants to be able to predict Saturday attendance at each attraction in order to assign its workers efficiently. Okay, so again, we're doing real life applications of slope and y-intercept and linear functions here. So it says the table gives attendance and rain forecast data for several recent Saturdays, and we kind of already covered that. And it's asking us what equations model the relationships of Big Fun and Get Real attendance to the probability of rain. So we're going to use this table to be able to come up with equations. Okay, we're going to have two separate equations. On one of them, the probability of rain is going to be your x, and the attendance is going to be your y. And on the other one, same thing. The probability of rain is going to be the x, and the attendance to Get Real is going to be the y. So we're going to have two separate equations, okay? One for Big Fun and one for Get Real. And then it also asks for what probability of rain will one attraction be more popular than the other. So this is where we're going to wind up using our inequalities, greater than and less thans, to be able to completely answer that question. So in problem A, it says use the table to find linear functions or come up with the equations relating the probability of rain P to the following quantities. Saturday attendance F at Big Fun. So we're going to have an equation that starts out with F, and we're also going to have one that starts out with R for Get Real. And we've broken the table out separately now, so you have one table for Big Fun and one table for Get Real, and come up with an equation for each of these tables. Part B, use your functions from question A, your equations from question A, to answer these questions. Show your calculations and explain your reasoning. It says, suppose there's 50% probability of rain this Saturday. What is the expected attendance at each attraction? So to help you out, I kind of gave you a little bit of information here. So if P is 50, what are F and R? So you're going to use each of your equations and plug 50 in for P. Okay, and then find out what the attendance is for F and R. Then part 2 is, suppose 475 people visited Big Fun one Saturday. Estimate the probability of rain on that day. So this time, you're going to plug in 475 for F and find out what P, solve for P. And that's just for the Big Fun equation. You don't have to do anything with Get Real on that one. Number 3, though, what probability of rain gives a predicted Saturday attendance of at least, another inequality, at least 360 people at Get Real. So now if R is 360, determine what P is, and then understand what direction that table is moving, or this equation is moving, so you know how to apply your inequality to that. Number 4, is there a probability of rain for which the predicted attendance is the same at both attractions? So is there a place where we can have F equaling R? And if so, what is P for that? Again, our aces for this 2.5 are 26 and 31 through 34. Let me know if you have any stuck points or questions in class.